Hi, and welcome to the first lecture unit in the new lecture chapter on support vector machines. So support vector machines are one of the most well-known and well-studied linear and nonlinear machine learning algorithm. In this lecture unit here, I'll introduce the linear hard margin SVM as a kind of a preliminary what comes next. So what is usually being used is what is called a soft margin SVM, and we need a couple of minutes to understand what that actually means. So I'll here introduce kind of a preliminary version of the thing for separable data, and also use this as a motivating point to discuss and introduce the fundamental maths and concepts and so on. So let's start. So what I want to study here in this lecture unit and also for the next couple of lecture units is a sound geometric principle to construct binary linear classifiers. So I'll do this now from a geometric perspective, but later on in a few lecture units we'll also connect this very well to our principle of regularized risk minimization, and we can actually see that the support vector machine has a very tight connection to that principle. And when Vapnik introduced this, this was already directly founded upon this principle of risk and regularized risk minimization. But give me a few minutes until we arrive at that stage. Let's now do the following. So we want to kind of forget everything we know about logistic regression or linear discriminant analysis. We'll try to construct a linear classifier for binary classification now from scratch. So let's assume that we have some data in front of us. It's linearly separable, so we can squeeze a hyperplane in between the two classes, and we now want to come up with a criterion which of these separating hyperplanes is actually best. And our criterion is going to be the boundary between the hyperplane and the next kind of the nearest neighbors on both sides to the hyperplane, and these guys here will later on call support vectors. And this width here of this boundary we're going to call the margin, and the size of it we're also going to call the margin. And it's kind of intuitive, reasonable to us that this margin here should be as large as possible, because this data here, this is going to be random, right? This is going to be sampled from a distribution, and of course, the exact locations of these points are going to fluctuate somewhat. And the smaller this safety margin is, the more likely it seems that we might actually accidentally misclassify a point. So how about now like using this as a mathematical criterion and trying to figure out whether we can actually compute this optimal hyperplane based on this maximal margin principle. And that's actually not too difficult, and I'll show this here in the next 10 slides. So let's try to formalize this now. So we'll assume we have labeled data in front of us, as always, n instances here. I'll now assume that my binary labels are encoded with +1 and -1, and I'll assume that the data for now is linearly separable. And by that I mean that I can use a linear classifier, f of x, which is theta transpose times x plus my intercept, and I can squeeze that in between the data so that every point is classified correctly. So I'll now introduce the so-called positive half space. The positive half space are all of the points where the score of this linear classifier here is positive, and hence all of these points are going to be classified as positive. And then there's the negative half space where the scores are negative, and I'm assuming, because of this linear separability, that it's possible to construct such a hyperplane to find such a scoring function so that all of the positive guys are lying here in this positive half space, and that all of the negative guys are lying here in this negative half space from my training data. And as we already discussed, there is a nice abbreviating way to state that we are classifying all of these points correctly so that they are lying in these respective half spaces. And this is just by computing the product of our +1 -1 label with the score. And if this is non-negative, if this is positive, then of course I'm classifying correctly, because then the signs of this guy here and of this guy here must be equal, and therefore our classification must be correct. And if it's unequal, then this here will be negative, and then the classification will be incorrect. So, and now hopefully you still remember from, I don't know, your mathematical education in school or from elementary linear algebra, that you can easily compute from the location of a point, which is a vector itself, and the formula of the hyperplane, which is here also this formula of our linear classifier, with the orthogonal vector of the hyperplane here being this theta. You can easily compute the orthogonal distance from a certain point to the hyperplane by computing through this formula here. So you can already see that the score of your linear classifier is nearly the distance to the hyperplane. The only thing we have to do to really make it the geometrical distance is to divide by the norm of theta. And if you would have assumed that this orthogonal vector here is of unit length, then the score would indeed be exactly the geometrical distance. But we're not sure that this here is normed, so we have to divide by the norm. And we'll also do this multiplication here with the yi, because now we have a signed distance where the sign actually also tells us whether the point is correctly or incorrectly classified. This is what we discussed exactly a couple of seconds ago. So if you would leave this out, this would still be a signed distance. Then this distance would tell us whether we are in the positive or in the negative half space. So whether we are in the half space that the orthogonal vector points towards or does not. So if it's in the same half space that the orthogonal vector points towards, we would be in the positive half space. But by multiplying here with the yi, this sign tells us whether the classification is correct, and that's a little bit more useful for us here in machine learning classification. So, we can now interpret here the length or the absolute value of that guy as the geometrical distance and the sign as correct or incorrect classification. And what we now obviously want to consider, if we are talking about this size of the safety margin, is the minimum distance of all points to this hyperplane. And this minimum distance I will call gamma from now on. And this is exactly now the length, the width of our safety margin. So we're actually only measuring this distance here. Yeah? So in a certain sense, you could also say that 2 times gamma is the width of the safety margin. But from now on, we'll only measure this here. So this I will define as the half width, so to speak, of the safety margin. And of course, if the data is linearly separable, then gamma here must, of course, be positive. And what we now want to do is we want to actually maximize gamma. So what we want to do is we want to find the minimum. So for a certain function f, which is a hyperplane, we compute the minimum distance of overall points. And this guy we now want to maximize with respect to f, so with respect to our parameters theta and theta 0. So you can actually write down the optimization problem we want to solve as maximize this minimization problem here. I want to state this already in a slightly different form because this is a little more convenient for us later. So I can also state exactly the same optimization problem in this form here. So in order for me now to maximize the margin, I want to say that all points in my training data set should have a distance to f of gamma or more, and I want to maximize gamma. And this will now maximize the margin. So what can we now do next? We can start, so we are not maybe completely satisfied here with this maximization problem. So first of all here, this gamma, this is such an expression here that doesn't look too convenient for us in terms of optimization. And then also here we have all of these inequality constraints that might be doable, but it's also, maybe we can simplify things a little bit. So let's try that. So first of all, what I want to do is I want to write this down here in slightly expanded form. So for now, I have only inserted here the functional form of my scoring function or of my hyperplane. So this is just how f looks like. And in this chapter here, I might sometimes write the scalar product here in this bracket notation, because this is quite convenient for us later if we want to kernelize the whole thing. So this here just means theta transpose times xi. So now we'll now begin to slightly rearrange this. So the first rearrangement I will want to perform is just simply multiply all of these inequalities here by the norm of theta. Okay, that was very simple. And the next thing, and this is a little bit more subtle, so let me explain this slowly. So the next thing we should note is that if we look at this optimization problem here, this is in a certain sense not really nicely uniquely defined, because it's very obvious that there's a lot of different hyperplanes that all have the same quality, because there's an infinite amount of different representations of the same geometric hyperplane. And the reason for that is if you write down a hyperplane, for example, like this here, and now you consider all of the points that lie on that hyperplane. That's a set of points, and that describes the geometric object, right, of the hyperplane. And you now multiply your formula, your mathematical algebraic representation of the hyperplane here with this c constant, and you simply assume that this is not zero, then you will arrive at exactly the same set of points. So there is an infinite amount of different algebraic representations which all encode the same hyperplane, and which, because of that reason, all will have the same quality in terms of optimization problem. And that seems a little bit inconvenient. So how about we now ensure uniqueness of our solution by kind of picking out a certain reference hyperplane from this infinite set here. So the only thing that we are now doing is that we are picking a certain scale of the hyperplane. Okay, so we're basically scaling the whole thing. So we are scaling this, mainly scaling this orthogonal vector theta here. So we're kind of picking a certain length because all of these guys here have different lengths of their associated orthogonal vectors. And I will now pick the length 1 divided by gamma. So for all of these hyperplanes, for all of these representations here that all encode the same hyperplane, there is of course now one point, at least one point, that has this minimal distance to the hyperplane, and this minimal distance is called gamma. And I'll now scale the norm of theta, so that's exactly 1 divided by gamma. And the reason why I'm doing that is because now, as you can have a look at that expression here, this very nicely now cancels out with this gamma, which is here already there, and turns the right-hand side into a 1. So that already simplifies things. And so I've now gotten rid here of this gamma, and hence of this expression, which is inconvenient for me. And now the gamma is still here, but I already now know that gamma is also, again, that gamma is, that norm of theta is 1 divided by gamma. So I know that gamma is actually 1 divided by norm of theta. So let me now insert that here as well. And the last rearrangement I now have to make is that I simply have to see that instead of maximizing this guy here, I could also minimize the inverse. So I could minimize the norm of theta, and then I can also see that instead of minimizing this guy, I could also minimize its square, or 1/2 divided, or 1/2 times the squared norm. So these are all simple transformations. So this is by inverting, I just turn a maximization problem into minimization problem, and these other transformations here, just monotonous transformation or isotonic transformations. So they don't change anything in terms of the solution set of my optimization problem. In a certain sense, all of these optimization problems are equivalent to me, so I can just pick the one that is most convenient for me. And this here is quite convenient, because if I look at that structure, that begins to look familiar, because first of all, I can now see that this is a convex optimization problem, which is already very nice, because that usually implies uniqueness, or at least if there's a couple of solutions there, they all will have the same quality. So that convexity basically means I don't really have to worry about stuff like local minima and so on. So why would I call this here convex? Because here I have this very, very simple quadratic objective, and I have these linear inequalities. So this is a quadratic form, a very extremely simple quadratic form, that I'm optimizing here over this simplex of linear inequalities. And there's actually standard solvers available for these types of problems. There's actually a huge amount of mathematical theory available that I can apply to this, and we'll study all of that in subsequent lecture units. And we actually will not, traditionally we'll not really use a ready-made solver for these types of problems. So we'll kind of construct specific optimizers for the support vector machine problem in order to exploit the specific structure a little bit more. But in principle, you could actually now use a ready-made solver for convex optimization for this problem. And this problem is also usually called a primal problem. Primal just means it's kind of our direct problem that we have in front of us. The reason why we give a name to that problem is because there's also a dual problem, and what that is we'll see in the next lecture unit. And this here, exactly this formulation, I will now call the linear hard margin SVM, as called linear because I'm constructing a linear classifier. As you later will see, we can also kernelize the support vector machine, and that gives rise to a whole class of nonlinear classifiers and also potentially nonlinear regression mechanisms. And it's called hard margin because for now we are assuming linear separability. Otherwise, this thing here doesn't make sense, right? So all of these inequalities assume that it's possible to completely separate our training data. And this we will also relax this assumption, or this assumption that the data is of that structure. We will relax in 2 lecture units. Okay, a couple of comments also on the name support vector machine. Apparently there's support vectors involved. So what does that mean? So with support vectors, we now want to label or want to name certain instances on our training set. So as we already discussed, we have this safety margin here, and the safety margin is the distance to the nearest observations in terms of the orthogonal distance here to our hyperplane. And of course, there must be at least 2. So there must be at least 1 point here for the positive class and at least 1 point for the negative class that exactly assumes this distance gamma. And because we know that gamma is exactly 1 divided by norm of theta, we know that the score of these points is exactly 1, or the absolute value is exactly 1. So yi times s, f, is exactly 1, because also all of these points have to be correctly classified. Yeah? So for a positive point, the score is exactly 1. For a negative point, the score is exactly minus 1. And the product here of the score with the label will be plus 1. So these points fulfill our inequality constraints here with equality. And exactly these points, so all of these points here, or the indices here, where the inequality constraints are fulfilled with equality, the associated training data points will call support vectors. And they're called support vectors because in a certain sense they span and define exactly the position here of my hyperplane. And I will actually prove that pretty formally later on, that they really span, also in a linear algebra sense, the structure here of my hyperplane. But for now, it should be okay for us to simply accept the fact that if you would now geometrically remove all of the non-support vectors here from the positive and from the negative class, and you would solve now the same optimization problem with a reduced set of points, only keeping, for example, these 3 guys, it's immediately obvious you would still arrive at the same solution, right? Because these guys here, they kind of constrain the position of the hyperplane perfectly. So you could not arrive at any other solution. In order for us to arrive at a different hyperplane, we would have to either delete one of these support vectors or actually introduce a new point that's here inside of that safety margin. Okay, this is it for now. This concludes the first unit.